Hi everybody, welcome back to Physics 142. We've been talking about circuits that contain capacitors and circuits that contain inductors. And we realized in the last video that capacitors and inductors in some sense are sort of opposites to each other. So we had a couple of circuits, and here's sort of one of those circuits. It has a capacitor in it, a resistor, power supply, and a switch. Here's our circuit with an inductor in it. And we realized right after you close a switch, a capacitor essentially has zero resistance to it, right? You're going to have lots of current that flows onto the capacitor. All the charge wants to flow onto that capacitor. So you have full current right away, but after a long time, that capacitor gets charged up, and once it's charged up, no more current wants to flow, and so functionally, it's acting sort of like an infinite resistor. Inductors, on the other hand, sort of work the opposite way. So for the inductor, right after you close the switch, there's a big change, and inductors don't like change. They fight change, right? And so they're going to resist that change sort of as best they can. So they're going to function as sort of effectively an infinite resistor, and there's going to be very little current in this system right at the beginning. But after a long time, the current's going to slowly build up. And once it's built up to sort of its full amount, then it just is flowing at its full amount, at current I. And inductors like things that are steady, not changing. So once you're at full current I, then it doesn't provide any more resistance. It just says, great, keep going exactly as you're doing. And so after a long time, it sort of has zero resistance, right? It doesn't provide any resistance, just wants things to keep flowing. So we have these sort of two opposite things, and in this video, we're going to ask, well, what happens if you put them together? All right, what happens if you have a circuit that has both an inductor and a capacitor in it? Now, before I get into that, I just want to remind you of a couple other things that will be useful for this discussion. All right. First of all, we know that on a capacitor, we can calculate the potential across that capacitor using the charge on the capacitor and the capacitance. All right. And we realize that we can calculate the potential across an inductor by looking at how the current is changing and the inductance. All right. We also had formulas for the energy in a capacitor, that the energy stored in a capacitor depends on the charge that you've put on the capacitor. And we had a formula for the energy stored in an inductor. The more current you run through an inductor, the more energy is stored in that inductor. All right, so these are sort of four important equations for capacitors and inductors that we will use shortly. The other thing that I want to remind you of is I want to go way back to actually the first thing that we did in Physics 142, where we talked about springs and oscillating systems. And you might remember that, we could write down Newton's second law, right? Remember Newton's second law? It's been a little while since we thought about that, right? And we realized that for springs have this Hooke's law, this force law that says the more you displace the spring, right? The more you displace the spring, the stronger the force is, and it's a restoring force, right? So we wrote that as minus kx, where k here was the spring constant, right? Remember all that? And so we could rewrite Newton's second law. We said, all right, Newton's second law is sum of all the forces, so we added up, the force was the spring force, right? And then mass, acceleration, we said, well, acceleration is two derivatives of position. So we could write that down as a second derivative of position, and we sort of got this differential equation here, right? That has the derivative, well, actually the second derivative of position, right? And the position itself in it. So, we wrote it down, and we didn't solve it, or, we didn't really, I guess, I didn't show you how to solve it, but I made an argument that said, well, what you need some sort of function that if you take two derivatives of it, you get that function back maybe with the difference of a minus sign. And so we realized that cosine was a great function, right? If you take the derivative of cosine twice, you get cosine back. And so we realized that an object that obeys this force law, right, that obeys this version of Newton's second law has the following motion. We said it's A, the amplitude, times cosine of, did anybody remember, of omega t plus phi, right? That was our sort of solution for the motion here, where A, remember, the amplitude is the maximum displacement, right? So I could also call that something like x max, right? And omega, you'll remember, is the frequency of oscillation. And we realized that that was the square root of k over m, that it was related to how stiff the spring was and the mass on your spring, right? That was how you could calculate omega. And this, you know, you could treat this as a little bit of exam review right now. I just sort of want to bring this idea of harmonic oscillators back into your memory because it might be relevant shortly. So let's just, you know, keep that in the back of your mind for now. All right, so that's a lot of background, but now to the question at hand. The question on hand is, what if you have a capacitor and an inductor, right? What if you have L and C in a circuit, all right? What if you have an inductor and a capacitor in your circuit? And so I'm going to draw you a circuit that looks like this, all right? So let's think about this. So I'll have a power supply, and my circuit's going to be a little funny. This is not going to look like maybe a circuit that you've seen before, all right? But I'm going to have a couple of switches. Technically, I only need one, but maybe it makes it clear if I have two of them, all right? So I'll put a couple switches in, and here's what the switches will look like. Oh, whoops. I want to put a capacitor right here. There we go. All right, so I have a power supply, V, all right, supplies some potential here. Then I'm going to have a switch, all right, a switch that can switch back and forth here, all right? It can connect on one side or on the other side, and I'll have another switch down here that can do the same thing, all right, that can connect on this side or on this side, and I'll operate them together, all right? So they go here or they go here. And then over on this side, I'm going to just have an inductor in my circuit, all right? So here is an inductor, and inductance L. And so here's the idea, how this is going to work, is first what I want to do is I want to have these switches, I'll connect them here, and the capacitor will be connected to the battery, or the power supply. All right, so we connect the capacitor to the power supply, and what's going to happen? Well, what's going to happen is, you know, charge will flow off the power supply and will charge up the capacitor, right? The capacitor will get charged up over time. That's good. So then we have a fully charged capacitor, all right? Once we have a fully charged capacitor, what I'm going to do is I'm going to take both these switches and switch them over to the other side, all right? And so now you'll end up with a circuit that looks sort of like this, all right? So this is sort of, you know, step one, right? Step one here. Then I'll switch my switches over here, right? Whoops. And so here's my capacitor. My capacitor is now fully charged up, right? It's got all kinds of charge on it. And here's my inductor, like this, all right? So now I have a circuit that looks like this, and so you'll see my circuit now just has a capacitor that's fully charged and an inductor. So this right here, this circuit is called an LC circuit, right? Because it has an inductor L and a capacitor C. And so what we want to know is, well, what's the behavior of this LC circuit? So to think about the behavior of this LC circuit, we're going to apply Kirchhoff's loop rules. All right, so let's, you know, pick a spot here to start and draw a loop here. We'll do a loop, and so let's think about the potential changes here. All right, so when you go across the capacitor, I'm going to gain some potential here, right? And how much potential will I gain? Well, I will gain, so we're applying Kirchhoff's rules, right? And so we'll do Q over C. We gain that potential. And then, right at the beginning, there's no current. And then, if you connect this, right, the charge is going to want to start trying to flow from positive to negative, right? So then you'll start getting some current. And so the inductor will oppose that. So we'll have minus L di dt equals 0, right? Because this is the formula for potential across an inductor. And we're going to, if you're increasing the current, then the inductor will make you lose some potential, right? All right. Now, this has I's and Q's in it, and we want to be able to sort of relate current and charge, all right? And typically, the way that we relate current and charge is we just say that, well, current is the time derivative of charge, right? It's how the charge is changing. Now, there is one little trick here, is that when we write it this way, like if we're thinking about the charge on the capacitor, all right, then what we think of as happening is usually we think of this being a positive sign for when the capacitor is getting charged up. If the capacitor is losing charge, but we're gaining current, then I need to put a minus sign in this equation, all right? So if we're discharging the capacitor, so we're losing charge, then we're going to have minus dq dt is equal to the current, because the charge on the capacitor is going down and the current is increasing, right? All that charge on the capacitor is going into the current. So we put the minus sign in. So this is sort of for charging, right? That was when we had our switches hooked up over here. When we discharge, we're going to put in a minus sign, all right? Okay, well, if we know this, if we know that charge and current are related, I can take and I can plug that into this equation, right? So I'll do that. So now we have Q over C minus L times the derivative of the current, and well, the current is minus dq dt in this circuit, right? So that equals 0. And so now I can write this, right? Sort of one more step here is, I guess I'll write it right here. Now we have Q over C. Minus minus is going to become a plus. And then we have L, and we have two derivatives, right? The second derivative of Q here equals 0. And I could just take that, and I'll do that. I'll rewrite that as the following. I'm going to move the Q over C to the other side, and I'm going to divide both sides by L. And if I do that, I get the second derivative of Q is going to be equal to minus Q over LC, right? So we moved the Q over C over here, so it became minus, then we divided by L. And what I'd like you to do now is I'd like us to sort of look at this equation a second. And what this says is that the amount of charge on the capacitor is related to, oops, I forgot a little square there, is related to the second derivative of the charge, right? How the current is changing. And what I want us to notice is that we've seen equations that look like this before. I have them written down up here, right? This looks exactly like the harmonic oscillator equation, just instead of X, we have Q, right? And instead of minus K over M, we have minus 1 over LC. And so what that means is that to solve this equation, if we want to think about Q as a function of time, right, how much Q is on that capacitor as a function of time, we're going to solve the equation using differential equations the same way that we solved the harmonic oscillator equation. And what we need is a function that when we take two derivatives, we get the same function back with a minus sign. And well, what is that? That's cosine. And so the answer, just like with the harmonic oscillators, but now with Q, is going to be the following. We're going to get Q of t, all right? Q of t is going to be the maximum amount of Q. I'll call that Q max times cosine of omega t plus phi. All right, just the same thing. You're going to have an oscillating system here. Now remember here, omega was the square root of k over m. So what is our new omega going to be here? What's our new omega going to be? Well, if we noticed here that k over m is functioning sort of similarly to 1 over LC, right? And so the new omega here, I'll move my board down, get just a little bit more room here, right? The new omega is going to be, if it was the square root of K over M, no, it's going to be the square root of 1 over LC. And so what we've arrived at here is that if you put a capacitor and an inductor together in a circuit, what you end up getting is a system that oscillates back and forth. You get a system that functions mathematically as a simple harmonic oscillator. And so you might remember at the very beginning of the semester, we started with harmonic oscillators, and something I said is that, well, in physics, there's sort of a joke that everything's a harmonic oscillator. And, I think this sort of makes it come full circle a little bit, right? We've been in the depth of circuits and all kinds of details about EMF and potential and induced current and self-induction, all that kind of stuff. And what we get out of all of it in the end is just a simple harmonic oscillator, all right? Where all the math is the same. It all functions as a simple harmonic oscillator. So what's going on physically? Well, physically, what we have is all the charge is on the capacitor here, right? But then that charge is going to start to flow off the capacitor, right? You connect a wire across the capacitor, it's going to want to discharge. And so over time, you'll discharge all of the charge on the capacitor, and at some point, you'll have all current and no charge, right? You'll have taken all the charge, and all the charge will have flown off, having some struggles here, right? All of the charge will flow off. It will flow off, and then you have a bunch of current going through the inductor, right? Once all the charge is off, that means you have a lot of current here, all right? But that charge then is going to kind of keep flowing over to this side, so then you'll start piling up the charges over here, right? And so then you'll go from having it charged up on this side. Eventually, it'll all be charged up on this side, right? The sort of sign will flop, all right? And you'll be back to all charge and no current again. And so what happens is you sort of alternate back and forth from having lots and lots of current and having lots and lots of charge, all right? And what happens is the energy in the system here is actually sort of conserved. So let's think about how that's working, all right? If we think about the energy in the system, and I'll make just a little bit more room here, all right? See if we can understand this a little bit better. All right, when we did harmonic oscillators, we said energy, right? Energy is conserved, and we said energy is K plus U, right? It's sort of potential energy plus kinetic energy. So, and we could write that, right? We said the total energy on a harmonic oscillator ended up being 1/2 K times the amplitude squared. All right, this is little k, right? The spring constant. And that was 1/2 mv squared plus 1/2 kx squared, right? So depended on the energy in the spring and the energy of motion, right? And you might remember, maybe I'll just sort of sketch this over on the side, right? When we had our spring box on it, right? When it was sort of fully compressed this way, then you have all potential energy, right? And 0 kinetic energy. But then once you release it, when it hits its equilibrium point, it's all kinetic energy and no potential energy, right? And then it stretches out over on this side, and then you're back to all potential and 0 kinetic, right? And so you sort of went back and forth from potential to kinetic to potential, right? That's the idea of a harmonic oscillator. Well, how does that work out for capacitors and for inductors? Well, a capacitor is, in this case, functioning a lot like the spring, right? We said the energy of a capacitor, is that still visible, my video? Oh, I'll move it down and then you can just barely see it. There we go. All right. The energy of the capacitor here is 1/2 times, instead of K, we're going to use 1 over C times Q squared, all right? And that acts a lot like potential energy, right? It's storing potential energy. But then for inductors store their energy through moving charges, right? And so that's a lot like this, 1/2 mv squared here. All the charges are moving through the inductor, and that's when this charge is stored. So that's 1/2 Li squared, all right? Where I is a lot like V, right? It's the moving charges. And when we add that together, well, that ends up being 1/2 times 1 over C times the amplitude is just Q max, right? However much charge you put on that capacitor to begin with. So what happens is you go back and forth between energy stored on the capacitor and energy in the inductor, right? Energy on the capacitor is just all the charges stacked on it. Energy in the inductor is from the moving charges. Wow. All right. That's fun. There's one other thing that I should say about this, all right, is that energy stored in the inductor ultimately is energy stored in magnetic fields. Right? You have moving charges, those are creating magnetic fields. Ultimately, the energy is stored in magnetic fields in the inductor. In the capacitor, right, the energy is all in the electric fields in the capacitor. All right? The energy here is in the electric fields. So what we have in this circuit, in this LC circuit, is you're going back and forth between electric fields and magnetic fields. You've got a bunch of energy in electric fields and a bunch of energy in magnetic fields. And that, I think, is pretty cool. All right, last thing that I should mention about this is, well, what happens if you put a resistor in the circuit? All right, so what if we take this circuit and now I want to add a resistor? So maybe I can do that. Let me just draw the circuit here. So we still have our capacitor, all right, and it's hooked up, but now we're going to add a resistor to the system, all right? So we have our capacitor, our resistor, and we still have our inductor, right? We're adding a resistor. What happens when we add the resistor? All right? Well, resistors, they resist current, all right? And so what resistors functionally do is that resistors add damping to the system, all right? Resistors add damping. So what does that look like? Well, you might remember damped harmonic oscillators. All right, let's move the board up here so we get a little bit more room. All right, so what did a damped harmonic oscillator look like? Well, the equations that we had for damped harmonic oscillators was that x of t was the amplitude. I'll call that x max. All right, the amplitude times e to the minus bt over 2m times cosine of omega prime t plus phi. All right, so remember b was this damping coefficient, right, this damping constant. And so what it did is it caused this sort of exponential decay, right? So that your oscillator, rather than just oscillating up and down forever, right? Your oscillator in a damped system oscillates smaller and smaller and smaller each time, right? And you might also remember that omega prime, the other thing it did is it sort of changed the frequency of the oscillation. Right? So we had a formula omega prime was not just the square root of k over m, but it's actually a little smaller, right? We ended up subtracting off minus b over 2m quantity squared, right? That was how that worked for harmonic oscillators, was that the omega changed a little bit, it got squished a little bit. So by analogy, how does this work for our RLC circuit? All right, well, for our RLC circuit, we write this formula. We're not interested in position. We're thinking more about how much charge is on the capacitor. And so then what we write down is we have Q of t, all right, is Q max times E to the minus, and well, the damping here ends up being the resistance, all right? And you'll notice that, M and L are sort of functioning the same way. Right? So this ends up being minus R over 2L times T, all right? And then cosine of omega prime T plus phi. And the new omega prime, all right, is, well, rather than K over M, we said that's 1 over LC, right? And then this B over 2M, well, that ends up being R over 2L squared, all right? So very similar, we're just using sort of different variables. The resistance is now functioning like the damping, right? The L is sort of functioning like the mass, right? L is functioning like the mass, and K is functioning like 1 over C. And so a damped RLC circuit, it will have, you'll still oscillate back and forth, but those oscillations will die out over time because the resistance is going to sort of remove some of that. It's going to, fight against that. And so over time, your oscillations will die out when you have an RLC circuit, when you add a resistor in there. So anyway, hopefully this is interesting to you. It sort of brings together everything we've been doing with circuits, and we realize that we can actually end up representing a lot of that with the math of harmonic oscillators, which is a lot of fun. So hopefully this has been fun to sort of bring some of these concepts in the semester together. I have one more thing I'm going to do in the next videos that will also bring just a few more things together, connect back to waves, and that will do it for Physics 142. So thank you very much.